Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, basically in the last lecture, if you recall, we were talking about the forces as well as the moments, internal moments, okay, which are getting developed in a particular cylinder member. And there we have seen that if you have the loading in xy plane in the cylinder member, then basically you will be having axial force, shear force and the bending moment, right. And then we took one example problem like this. So, one simply supported beam AB is resting on supports A and B. Okay. Based on that, we calculated reaction RA and RB, and of course, the beam is experiencing one concentrated force W at the point D, and we considered two different sections to define the shear force as well as the bending moment, okay, for the whole beam, section CC and section C prime C prime. So, section CC is spanning from 0 to A, whereas section C prime is spanning from A to L, right. Okay. And we have got the shear force and bending moment by satisfying the equilibrium condition, and we have got V and MB. So, like this. So, V is equal to W minus WB by L at section CC, whereas MB equal to WB x by L, and similarly the shear force and bending moment, okay, can be expressed in C prime section like this. Now, if you look at the expression for shear force and bending moment, basically the variation is linear, right. If you try to plot the shear force versus shear force in the x axis and along in the y axis, sorry. So, shear force along y axis and along the x axis, if you plot, x axis means the beam is spanning in the x direction, right. So, what I mean to say that if you try to get the variation of the shear force along the whole beam, okay, then that variation will be very much linear, as you can see, because these two sections will define the state of shear force as well as the bending moment completely for the whole beam, right. So, if you look at the shear force expression, so that will be also linear in x. Similarly, the bending moment expression is also linear in x, right. So, now it is very much advantageous most of the times, and therefore, people do that, people follow this procedure, that you get the variation of shear force and bending moment, okay, for the whole beam, and that variation is known as shear force diagram and bending moment diagram. In short, we will be calling that thing as SFD, that is shear force diagram, and BMD, that is bending moment diagram. And these two diagrams will be very much handy for a design engineer, which will talk about the complete variation of the shear force and the bending moment for the whole beam. Okay. Now, let us, because all the times you cannot, or you may not like to express or find out the value, okay, from these expressions, of shear force and bending moment. Rather, you try to get the picture of the variation, okay, how it varies, how the shear force is varying over the whole beam, how the bending moment is varying over the whole beam. So, this picture will give you much more exhaustive say detailing, okay, about the analysis. Okay. So, now let us draw the shear force diagram first. Okay. So, this is my SFD. So, this side, so this is my baseline, okay, this solid line is my baseline. So, now if you look at for section CC, so section CC is varying, or section CC is valid rather, from this point to this point, right, from A to D, because it is varying from 0 to A. small a, right, that is shown here. So, from this point to this point, what is the value of your shear force? That is given by minus Wb by L, constant, right. So, if I say this is my baseline, so below the baseline it will be negative, that is my convention I am using, and above the baseline whatever we will be plotting, that is positive. Okay. So, it is coming negative, the shear force is coming negative minus Wb by L, and that is constant. So, this is Wb by L, okay. That is the variation of shear force from A to D, okay, constant variation, of course linear. And then at section C prime, that means that is varying from D to B, right, from this point to this point. And what is the value of shear force? Wa by L, positive, right, again constant. So, Wa by L, okay, positive, and this total will be W. You can add it and you can find it, because here actually you are getting the abrupt jump because of the application of this concentrated force. When shear force is becoming almost constant, okay, shear force is becoming constant from this point to this point, and suddenly you are applying some concentrated force here, so shear force will be getting one sudden jump, okay, and then this will be the variation, this will be the again constant variation from D to B, okay. So, this is known as shear force diagram, okay. In some book you will see that people to understand in a better way they hatch it, but I am not putting the compulsion to you, it is up to you. Even if you do not show that thing, there will be no problem, okay. So, they try to show this hatching, okay. In some book you will be getting that. Well, so this is your shear force diagram, okay. So, now if you look at this shear force diagram, basically the designer will understand, if you give this shear force diagram for this beam, so designer immediately understand, okay, so this is the variation of the shear force for the whole beam, and accordingly they will take or they will consider the design parameters, okay. Similarly, now if you try to draw the bending moment, okay, so this is my BMD, bending moment diagram. Now, if you put x equal to 0, if x is equal to 0, that means you are at point A. At that time, what is the value of your bending moment? That will be coming from this expression. If you put x equal to 0, bending moment is 0, okay. And if you put x equal to A, right, bending moment will be WABL, AB by L, right. So, at x equal to A, it will be WAB by L, okay, rather I will write later on, okay. I am just choosing the point like this. So, and the variation is linear. So, I am just connecting these 2 points, okay. And again at x equal to say L, your bending moment will be coming from this expression. If you put x equal to L, it will be becoming 0. So, from this point to this point again it will be linear. So, it is not looking like linear. So, let us get the actual linear line, okay. So, this is your bending moment. So, this WAB by L, okay. So, this is your bending moment diagram, understood. So, in this way we can get the complete picture of shear force variation and the bending moment variation for the whole beam. Now, if you look at this bending moment diagram, you are getting the complete picture about the variation. Now, the maximum bending moment is happening at this point, and the magnitude of the maximum bending moment is nothing but WAB by L. So, it is completely 0 at this support and 0 at this support, okay, and in between that it is linearly varying. So, this shear force diagram and bending moment diagram are very important aspects, okay, in the analysis of your slender member. Okay. So, now we considered here only the concentrated force, right. Now, instead of that, I mean sometimes you may have the distributed load. Suppose one, if you consider one beam and on top of the beam you have the slab or the roof, right. Okay, that roof will be generally giving the distributed load over the whole beam. So, if you have a distributed load over the whole beam, instead of some concentrated force, you may have the concentrated force, you may have the distributed load, okay. Any kind of loading you can have on the slender member, right. So, if you have the distributed load on the slender member, then how you can analyze that thing? Let us take that example and let us talk about that thing now. Okay. So, distributed load. So, if you have the continuous distributed load, say this is your say beam, this is your x direction, this is your say y direction, you have the continuous beam and you have the distributed load like that. So, this is the distributed load over the whole beam, okay, and we are now considering one small segment, okay. Say delta x, and this distributed load over the length delta x, I can consider some concentrated force, say delta F. Okay. Now, what does it mean? Let's talk about that. Therefore, the total force on a length delta x be denoted by say delta F. That is the total force. So, over a small length delta x, the total force is nothing but say delta F. So, therefore, the intensity of loading say del q can be written as limit del x tends to 0 del f del x, that is force for length so q is your intensity, okay, intensity of loading. So, intensity of loading can be given by this expression, very simple, okay. So, now so whenever you will be getting this kind of distributed load, so how you will analyze the system, okay. Now, let us talk about the most common type of distributed load, that is nothing but the uniformly distributed load, and in short generally we will be using that word, that is UDL, okay, uniformly distributed load. So, if you have the uniformly distributed load over the whole beam, then how it varies? Either it varies constantly, either the distributed load, say this is a beam, okay, either you have this kind of distributed load, constant distributed load with constant load intensity Q, okay, per unit length, or you may have this kind of loading linearly varying loading. Okay. So, generally most of the times we will be using or we will be dealing with this kind of distributed load. Now, if you have this kind of distributed load, how you will analyze the system? Okay. So, let us talk about that thing. We will take one small example to understand the process of analyzing, okay, this kind of distributed load. So, the example is one cantilever beam, okay, with linearly varying distributed load, okay, this is A, this is B. The total load equal to capital W. Okay. The total load means area of this triangular distribution, okay. The area under this triangular distribution is W, okay, and the length of the beam is say L. Now, if you want to draw the free body diagram, you just replace the supports. Here only one support is there. So, you replace the support, okay. This is my free body. So, there will be one reaction, say RB, and there will be one moment, say MB. I am not considering the horizontal force, that is x directional force here, right. So, this is your say y and x, okay. So, there is no reaction in the x direction because there is no external force applied in the x direction. So, therefore, I can ignore or I can consider that is 0, okay. So, these are the reaction forces and moments, and this extreme load intensity is say W naught, small w naught. Now, if I want to analyze this thing, what is my first step? I will be considering one section, right. I will be considering one section, okay, section say CC at some distance x away from the free end. So, this is your free end, this is your fixed end, okay, fine. This is some cantilever beam, you know what is my cantilever beam, right. One end is completely fixed, another one is hanging kind of thing. You might have seen this kind of thing in several civil engineering structure like your chaja or maybe the cantilever slab in flight, I mean aeroplane, you generally get the wing of the flight. So, that kind of structure is nothing but your cantilever structure, okay. Well, so I am considering one section here which is x distance away from the free end say A, this is my B, okay. Now, how we can get the reaction forces? So, your first job is to find out the reaction force RB and reaction moment MB. How you will find out? That you get from your equilibrium condition, okay. So, for that I can simply satisfy summation of Fy equal to 0. So, that gives me RB, okay, minus 0 to L, because this is varying and this is my say Wx, okay. So, Wx is nothing but the load intensity at x distance away from point free end A, okay, and that Wx, if you express in terms of this extreme load intensities, that will be W naught x by L, okay, fine. So, that we can express like this. So, this Rb minus 0 to L, okay, we are integrating that thing, Wx dx. Now, if you look at this, what is Wx dx? That is the concentrated force over a distance, over a small distance dx, as we just discussed now, right. We just now discussed, right. If you have a concentrated force delta F over a small distance delta x, right, then the load intensity is your limit delta x tends to 0, delta F by delta x, right. So, from that say condition you get this, right. So, if you integrate from 0 to L, you will be getting the total intensity. So, that is nothing but 0, okay. So, that gives me, if you put the value of Wx from this expression, you will be finally getting this is W naught L by 2. Now, what is this W naught L by 2? That is nothing but the area of the whole triangular load, is not it? Okay. So, now let us, because this is given, actually total load is given. So, if I know the total load, I can express W naught in terms of capital W. So, let us do that. So, your capital W is nothing but half into W naught into L. This is the area of the triangular distribution, and that is nothing but the total load. So, from there I can find out W naught is nothing but twice W by L, okay, fine. So, this is the load intensity at the extreme point, okay, that means at the fixed support, okay, at the support, okay. So, now as per our previous convention, now we will be considering the free body diagram of the beam, okay, which is coming left of this section CC, okay. So, if we consider that left part of the beam, and if I draw the free body diagram, that will look like this. This is V, this is MB, that is bending moment and shear force, and this is say x distance, okay. This is your section CC, okay, x distance away from the free end. Now, what we are considering to define this thing in a better way, we are considering one local coordinate system, say xi, okay, and we are defining, this is my xi, this is a small distance d xi, and this is your xi, okay. Therefore, this distance is x minus xi, okay. Some local coordinate system we are going to introduce, that is xi, okay. Within x, I mean this distance, x is nothing but your global coordinate system, but we are introducing one local coordinate system, that is xi, and this in this area your load intensity is W xi d xi, okay, where W xi can be obtained as W naught xi by L, because everything we are expressing in terms of W naught, because W naught we have got in terms of capital W, that is the total load of the triangular distribution, okay. So, we have got the expression of W I in terms of W naught. Now, from there if we take or if we satisfy summation of F y equal to 0, we will be getting V minus 0 to x W I d xi equal to 0. From there I will be getting V equal to W naught x square by twice L. That is the shear force expression, right. That is the expression for shear force in terms of x. Okay. Similarly, I can find out if I consider the moment equilibrium, I will be getting mb plus 0 to x w xi d xi into x minus I, which is equal to 0. So, from there I will be getting mb equal to minus w naught x cube by 6 L. Okay. Now, one interesting thing you might note, I mean already in the previous problem also we have noted it, whatever expression you are getting for the shear force, the bending moment is one order higher in terms of x, right. What is the expression of shear force here? W naught x square by twice L, that is quadratic equation. Okay. Whereas, if you look at the bending moment expression, that is cubic expression, one order higher. In the previous problem, whatever we had taken, in that problem the shear force was constant, right. Okay. It was not dependent on, I mean it was constant. So, x term was not there, but when we are talking about the bending moment, then that was linear in x. So, therefore, we are getting one order higher in terms of x, fine. So, that is very very interesting say phenomena, and later on we will be seeing that thing, that derivation of your bending moment will give you the shear force, something like that. So, that relation will be establishing. So, what I mean to say that whatever equation you will be getting for the shear force for bending moment, that equation will be one order higher in terms of x. Okay. So, now you have got the expression for mb. Now, I want to find out what is the value of mb, capital MB, okay, from this expression. So, capital MB means this, the support reaction. The support reaction is nothing but the bending moment, okay, at x equal to L, agreed or not. Your MB, the support reaction, right, moment reaction is nothing but the bending moment at x equal to L. So, if you put x equal to L there, then you will be getting capital MB is equal to minus W naught L square by 6. Clear? Fine. Okay. So, now we are going to draw the shear force and bending moment diagram. Okay. So, how it will look like? So, we are going to draw the shear force diagram SFD. So, this is your baseline. Okay. This is your baseline, point A, B. Okay. Now, if you see the expression, so only one section will be sufficient to define the complete variation of shear force, because here actually the load is, I mean you are not getting any change in load, this is a continuous load, right. So, therefore, only one section will be sufficient enough to define the whole bending moment and shear force characteristics of the beam, right. Okay. So, what was the expression for V? The expression for V was your in the that was the quadratic equation, that is a yes, that was the quadratic equation, that was W naught x square by twice L. So, if you plot that, so you will be getting so here it will be W naught L by 2, okay, and that was positive, and this curve is nothing but V equal to W naught x square by twice L. This is your shear force diagram. Okay. Similarly, if you try to plot your bending moment diagram, say this is my baseline, okay. Your bending moment equation, if you look at, if you recall the bending moment expression, that was in cubic form, right. So, therefore, at x equal to 0 that was 0, at x equal to L that should be minus W naught L square by 6, and in between it will be negative. So, this is your quadratic equation, MB equal to, this is minus, this is plus, minus W naught x cube by 6 L, and here this is nothing but your MB, that is W naught L square by 6. This is your bending moment diagram. Okay. I hope you have understood that if you have the distributed load like this, then how you can analyze or how you can find out the shear force diagram and the bending moment diagram for a beam. Okay. So, I will stop here today. In the next lecture, we will be talking about the resultant force, and then we will be seeing that how we can establish the differential relation between bending moment and shear force, and shear force and the loading. Okay. So, I will stop here. Thank you very much.